Our next speaker is Josh Frisch, and he will talk about computing Poisson boundaries without moment conditions.
Hi, everybody. Thank you for being here. I want to say what I will be talking about is based on two joint works. One joint with Kunal, who's right here, Behrang Forghani, and Giullio Tiozzo. And the second one is joint with Eduardo Silva. So I'm going to be talking about some boundaries and how one computes them. And I'm going to be talking about a certain recent sort of direction where we try and say, okay, like what happens to the boundary when you allow wild measures, measures where your jumps can sort of be arbitrarily huge, some reasonable fraction of the time. Before I get to this, I want to talk about what the Poisson boundary is, because I don't think everyone here has seen it, or at least everyone here has seen it in a way that they will automatically remember. I will say that when I give my definition, I'm basically giving the correct definition, but also, right, technically, if you want to make this correct, you might say things like, you take the ergodic components of something, but I won't worry about the distinction right now. So I want to start by asking sort of a question, which is, what does it mean for two paths of a random walk to be asymptotically equivalent? Right? And there's a lot of different notions you might come up with for asymptotic equivalence. You might try and come up with, stronger notions. You might come up with coarser notions. But I think you should agree with the following. If I have some trajectory, x1, x1, x2, x1, x2, x3, x1, x2, x3, x4, and some other trajectory, y1, y1, y2, y1, y2, y3, and so on and so forth. And there's two times, say this time and this time, such that the random walk, let's call this big one xn for n greater than 2. And this one will be ym, or n plus 1 for n greater than 2. If my trajectories are going to agree past some finite time, so basically what I'm saying is you remove some finite prefix, possibly two prefixes of different length, and then your trajectories are literally identical, then I think we should be able to call these random walks asymptotically equivalent. Right? Certainly, we say, if you're doing the exact same thing, except you do something different in the very beginning and you possibly have a time change, you're basically doing the same trajectory. All right. So this gives us the reasonable notion of the Poisson boundary of a group. Now, there's not really a great standardized notation for a Poisson boundary, so I'll just call it PB for right now. So, of course, right, you don't just have a group. You always need a measure too, right? Because a random walk is not, uniquely defined by a group or by a graph. You need to say what your step distribution is going to be, right? This is just going to be equal to the space of trajectories with the tail invariant sigma off right. Right, so what we're saying here is, right, you aren't allowed to ask about any event, you're only allowed to ask what the size of a tail event is, I guess I should say, and the random walk path measure. Right, so if you want to know, right, some Burrell event, you just say, like, right, for example, how many random walks start with A, B, it's just going to be mu of A, mu of B. If you ask for a more complicated event, right, this tells you what it is on the basic Clopin set, so you can just extend it. Right, so this gives you some reasonable notion of like what's a space of asymptotic events of a random walk R. And right, and I think this is, for me at least, somewhat inherently interesting. If you care about random walks, you want to know what can you say about random walks. It's also interesting because sometimes this is trivial, which is a very strong random 0-1 law. It says anything you could possibly ask about random walks, if an asymptotic thing to ask, is either always true or always false. It's a very strong statement. But the original motivation that Furstenberg had when he came up with this definition was, right, basically to give a Poisson formula, like in complex analysis, for the space of bounded harmonic functions. So what's a bounded harmonic function? Well, a bounded harmonic function is, first of all, a bounded function from your grouped as real numbers. X from G to the real numbers, which satisfies the following average property. F of X is going to be the sum of G and G of F of XG, mu of G. Mu of G just means the probability that you choose G here. So what this means is that, right, if I want to know the value of my function, I can just go one step forward and take the average. You might ask why these are called harmonic functions, but if you do, instead of, a standard random walk, you do Brownian motion. This recovers the notion of classical harmonic functions on, say, R to the D. You don't even actually need to do Brownian motion here. You could also just, for example, take a random walk anywhere in the sphere. Of course, then you'd have to replace your sum with an integral, but same thing. This is, right, a clear discrete analog of the notion of a harmonic function. And, well, Furstenberg observes the following really cool characterization of them, which is we have our space of bounded harmonic functions on G mu. Right, this is a nice Banach space. Right, it actually has a nice G action just by, that multiplication by G. The Poisson boundary has a nice left G action where you just take your random walk and you reroute it. So you take the path x1, x1, x2, x1, x2, x3, and send it to gx1, gx1, x2, gx1, x2, x3. And Furstenberg observed that the space of bounded harmonic functions on G mu is isomorphic to L infinity of the Poisson boundary of G mu. And in fact, not only is it isomorphic, right? It's isomorphic as a representation. The G, this intertwines the G actions, right? So if you want to understand bounded harmonic functions, you want to understand the Poisson boundary. If you want to understand the Poisson boundary, you need to understand bounded harmonic functions.
A small historical comment. I'm not sure that first, boundaries are even sometimes called with a reason of Poisson Furstenberg boundary.
Sure.
But the definition was introduced before, right? In the
Yeah, no, Blackwell was the original one to do it. I think for the right, do.
Had the theory of boundaries, not only for groups and some equivalents.
Right, well, was Furstenberg the first one to look at the G equivariant action on that, or was actually Blackwell?
It seems to be true.
Yeah. So. Right. Right, so my goal is going to be to compute some boundaries. Right, so let me give just sort of two classical examples. So I could have a free group. And on a free group, let's at least check that the Poisson boundary is non-trivial. Well, if I take a random walk on a free group, except when it's at the identity, 3/4 of the time you're going to move away from the origin, 1/4 of the time you're going to move towards the origin. Thus, eventually, if I take a simple random walk on the free group, I'm going to end up in one of the 4 corners. Right, I'll either end up when we're starting with A or B or A inverse or B inverse. Similarly, when I'll end up with a prefix of length 2, prefix of length 3, eventually my random walk is going to converge to some infinite word, right? A, B, B, A, B, A, B, or something. Just some infinite word was probability 1. And so this is clearly sort of some sort of thing. We can look at the convergence things here. We can look at all Borel subsets, and that's going to give us some, tail invariant sigma algebra. Obviously, what word you converge to is tail invariant. But it's a priori, I want to say, highly non-obvious whether this is everything. And let me bring up one more example. Right, this is the free group is obviously the prototypical non-amenable group. The prototypical amenable group, okay, it's probably Z. But if we want to look at sort of non-trivial ones that are not virtually nilpotent, one of the classical examples is the so-called lamplighter group. And ZD, wreath, Z mod 2Z. There is a notational disagreement about which goes on which side here. I apologize if you take the other convention. So what is Z to the B, wreath Z mod 2Z? Well, I want to tell you what it is sort of as a story. You have some person walking around in d-dimensional space, right? And with, probably let's let D be greater than or equal to 3. Of course, you could also do this for 2 or 1. Let's say we're actually just going to think about equals 3. So you have a person in a helicopter, and in their helicopter, at every point on the integer lattice in space, they can either turn on or turn off a lamp. Right, and of course, if you turn on the lamp twice, that's the same thing as turning it off. Right, so your person's going through space, turning on some lamps, turning off some lamps. Right, their move is maybe what they'll do is with 50% chance turn on or off where they are, make one random step, and then turn off or on where they ended. And this is a very reasonable random walk. We can understand it. This sort of gives you a group action. It's a fate, or it's a free group action, so it really does just tell you what the group is. And the question is, are there any tail events here? And in the early 1980s, Harmonic and Frisch observed that yes, there are. Namely, if you look at the lamp at the origin, that will eventually either be left on or turned off. Why? Because the random walk on Z cubed, or in general, any Z to the D higher, is transient, which means you only return finitely many times to the origin. You might then obviously ask what happens about Z squared or Z. And in these cases, right, right, because you're recurrent, there won't be a lamp left on. And in fact, the Poisson boundary is actually trivial here, which was sort of the main reason they found these examples. They show that for solvable groups, triviality, non-triviality of the Poisson boundary is really subtle. It's not, right? You have these groups which look the same, except one is sort of two-dimensional, one is three-dimensional. And like transient's recurrence, you get this dichotomy. All right. So how does one actually go about and compute a boundary? Well, with very few exceptions, I know of a few, but like really it's, maybe 1% of the literature. You need to assume that the Shannon entropy of mu, right? So mu is just some discrete random variable, so it has a Shannon entropy. We need to assume this is less than infinity. Right, this is just going to be, for people who haven't seen this formula before, this is just going to be sum of G and G with probability G times minus probability G times log the size is probability G. Right, this is not, of course, we can ask about how to compute things out, but really it's extremely, extremely difficult. And outside of like very restricted circumstances, we just don't know how. So why does entropy help you? Well, it helps you because of the following criterion. Kamenovich in 2000. Right? If I have finite entropy, I can look at the asymptotic entropy. So H of mu equals the limit as n goes to infinity of H of the nth convolution power of mu divided by n. Right? So instead of looking at just one mu, I take a power of mu and a power of mu and a power of mu and ask how quickly the entropy grows and then goes to infinity. Right?
It's have to mention this is definition of obvious, right?
Yes, this definition is due to events, yes. I'm not saying, it also, Vadim didn't invent this notion, right? The first version of sort of looking at entropy is not due to Vadim, it's due to Vadim and Vershik, who passed away recently, again, in the early 1980s. But for the criterion I'm going to talk about, this is due to Vadim. I see he had it earlier, but the main sort of public citation of it is in 2000. Right, so we have this. And then if you have some, boundary B, which you don't know whether it's a Poisson boundary, so this is going to be just some G invariant, sub-sigma algebra of, right, the Poisson boundary. We can look at the conditional entropy, H of mu conditioned on B, which is going to be the limit as n goes to infinity of H of mu to the n, conditioned on B over n. For people who haven't seen conditional entropy before, this basically just means you assume you know everything in B and then you ask what the entropy is. Right? And so Vadim showed that if this is 0, then B is up to null sets the Poisson boundary. So this actually gives you a way to compute the Poisson boundary just by sort of computing some entropies. And again, this is the main thing we were doing. So I wrote down some years here, so let me get them correct. Right, the first computation sort of Poisson boundaries, I'll just say if G is non-elementary, hyperbolic, the Poisson boundary, sorry, and mu is finitely supported. The Poisson boundary of G mu is isomorphic to the hitting measure on hyperbolic boundary. This is originally Ancona. Kamenovich sort of massively generalized this in his 2000 paper, right? So the generalization I want to talk about, well, first of all, he moved the class hyperbolic groups to a sort of vastly broader class of groups, right? So which are called so-called groups with hyperbolic properties. There's a plethora of examples of these. And the other thing he did is he improved the statement mu has, is finally supported. Mu has finite logarithmic moment, right? Which means that if you take, right, the average of the log of the lengths that exist, plus finite entropy. So we still needed some size criterion. The size criterion was pretty crucial to his method, but he did, right, was able to massively expand the class of measures where it works, from sort of just these very restrictive ones to this huge class. Now, what about for the lamplighter group? So I'm going to say this. I'm going to say the result of line present 20, but I want to be very clear that this was preceded by a result of Anna Oeschler in 2010, right? The basic improvement of lines pres is they do things in 3 dimensions in lines in Anna Oeschler. She does it in 5 dimensions under a more restrictive moment condition. So I'll actually just say, see, I want to focus on this one, right? If we have G, wreath H, and G, right, mu, and the random walk, and the projected random walk on mu is recurrent. Remember, we want that recurrence because otherwise sort of things are very complicated. Even in this classic case, right, you get trivial boundary. Then some boundary, right, and mu has the mu has finite second moment. This will imply finite entropy. Then the Poisson boundary G mu is the lamp configuration at infinity.
You wanted to bring the current or transient?
Sorry. Transient, of course. Thank you, sorry, right? You need it to be transient. Right, there are cases where you can ask about what happens when it's recurrent. Sometimes the boundary might still be non-trivial. This is a thing we're still actively thinking about. Right, but transience is sort of the more typical thing. This happens, for example, whenever you're not z or z squared. And then, right, the point is that your lamps are going to stabilize, and that will give you the Poisson boundary. But in all these things, right, the moment conditions sort of play a crucial role. You need to use the moment conditions pretty heavily. And there's a real question in forcing to use entropy, and there's a question of basically, do you really need that, or is that just an artifact of the proof method? So I will tell you the theorems now. And then I will try and do, at least with remaining time, give you a sketch of how it goes, at least in some circumstances. Right. If G x on x is acylindrically hyperbolic, I won't go into what this means. The example I will say is this is satisfied by a huge class of groups. For example, it's satisfied by mapping class groups. It's satisfied, if you take the right action, it's satisfied by out of n. It's satisfied by all hyperbolic groups. But I'm going to tell you to ignore that it's satisfied by a huge class of things and think about hyperbolic groups acting on their hyperbolic boundary, or even more concretely, thinking about free groups acting on, the space of infinite words. And U has finite entropy. Right. Poisson boundary. Right. Of G mu is going to be the hidden measure on X. So we do still need finite entropy here. Again, there's virtually no
moment assumptions.
moment assumptions whatsoever. That's the point, right? So you could a priori have like arbitrarily large gaps, right? Maybe with probably 1/2 to the n, you go 2 to the 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 n many steps on your thing, right? So these walks can be wild, they can be crazy. And then the second result, the one with Silva, right? Ask what happens.
Sorry, I've lost the theme. When is this false? When is this not the Poisson?
I'm saying when.
Are you proving it's true there?
Yeah.
Without any conditions?
Except for entropy, we need finite entropy.
Yeah, entropy. So, but is it possible that?
I have no idea whether entropy is necessary. This is one of the biggest open questions in the
Okay,
field,
all right, that was-
even for the free semi-group.
Okay.
I would love to know.
Even for free groups.
Okay.
Yeah.
Fürstenberg's lemma for any measure, right? Convergence will also.
All right. Okay. So that's the answer. Clear answer. Thank you.
Yeah, I would love to know. Right? And then we also have the theorem with Silva, which is that if I have G wreath H, so here I do need to assume, suppose the lamp configuration converges. Right? This is no longer automatic just from G being transient, because, for example, maybe you sometimes light a
What are you writing there? G free product H? What is
G
it?
wreath H.
H H.
Wreath H. Right? I mean, if you want, right?
Right. I was just trying to. I think. And what are G and H?
Yep.
They anything?
What?
G and H or
G and H are arbitrary. Right? But I am assuming that the lamp configuration converges.
Okay.
Right? Which again is automatic in, right, sort of for final first moment, but in general, with huge things, of course, might not happen. Then Poisson boundary, right? And I assume that mu, again, we need that it has finite entropy. All these things require finite entropy. Then the Poisson boundary of G mu is going to be the Poisson boundary of G times the lamp configuration. If G is, for example, zeta to the D, this term vanishes. So in the classical lamplighter thing, this vanishes. In general, I sort of suspect if you're non-degenerate, this should vanish. There's a few things you need to be careful about, like maybe the lamp configuration always converges trivially, right? Maybe you secretly just have a random walk on G and then you can't hope to get rid of it, but I suspect it vanishes more generally. Again, no moment condition whatsoever, but we do need finite entropy here. We don't know whether finite entropy is necessary for this either. What we do know is that you do need to suppose that the lamp configuration actually converges. There are examples where the lamp configuration doesn't converge, but the Poisson boundary is still non-trivial.
And in the most important examples, maybe like Z3 with a finite group, usually if you don't have a finite entropy, the boundary can very much be trivial, right? So
Yeah, the boundary can be trivial, it can be
the
non-trivial.
second result is more clear that entropy really is a good assumption.
Yeah, right, you do, right, the boundary can be trivial, the boundary can be non-trivial. So this shows us identifications and we don't need any moment criterions to pull these off. Right, really, this is just for sort of like arbitrary random walks. All right. Any question on the theorem statements? All right, so I'm going to, with my remaining time, try and give a sketch of how some of these look. I'm going to, right, simplify with wild abandon the classes of groups I'm looking at, right? Because I don't want to try and get into every single technical detail right now. And in fact, I'm not even going to look at a group right now. I'm going to look at the free semi-group. And then I'll try and talk about where the difficulties show up. So let's say I have an arbitrary measure on the free semi-group. Here, the fact that you converge to an infinite word is extremely easy. There's no cancellation. So of course you converge to an infinite word. But, right, it's still not at all a priori clear whether that's a boundary. And in fact, without entropies, this is still like a very famous open question in the area. So how, right, does this work? Well, here's the thing, right? If I want to know where I am at time xn, if I tell you what the infinite word I'm going to converge to is, right? Like it's a, b, b, a, b, a, b, something. How much more information do I need to tell you to figure out where xn is? Well, because it's a free semi-group, all I need to tell you is the length. Right? If I tell you the length, then I tell you where there is here, and of course there's been no cancellation, so the length uniquely specifies it. So but here's a key point. What is the entropy of the length going to be? It's just going to be a random walk on Z. Right? Right? The lengths here are actually additive. So first of all, you could just now cite Choquet and be done. Right? Right? The boundary is trivial for Z, therefore the entropy is trivial for Z. Right? And we're set. I'm going to try and give you a different argument for it because that's going to be the one that sort of generalizes. It's more hands-on, which is basically as follows, right? I have my measure mu, and I want to break it up into big parts and small parts. Right? Small and big. And what do I care, right? What do I actually care about big? I just want the, right, entropy of telling you if your increment is big, and if so, what it is to be less than epsilon. So basically I want to take the small things to be the mass of the entropy and the big things to be sort of the L1 small part of the entropy. And then if you assume you have a big thing, I will just literally tell you what it is. So now I'm going to look at the entropy, of mu to the n conditioned on, infinite words, as we always said, but now also conditioned on, the big increments. Again, I'm going to literally just tell you what things are big. And the point is that this entropy is small, This is going to be n times epsilon. So as we make epsilon smaller and smaller, we'll be able to get arbitrarily good bounds. All right. But here's the thing. If I tell you n times epsilon, you know what all the big increments are. The only things left is you need to sum up the size of the small increments. Small increments have some universal bound c in length. And so if I sum up a bunch of numbers less than c, if I sum up n numbers less than c, well, I get a number between 0 and nc. You see? And of course, for any distribution between 0 and nc, the entropy is, less than log of c plus log of n, which grows sublinearly. So we have something sublinear. We have something at most epsilon n, We're less than epsilon n for every epsilon. We win. Now, why did I do this? Why did I do this sort of very constructive thing? Because this is our general idea for hyperbolic groups, What are we going to do? We are basically.
Can you view this maybe, when you prove this bounded harmonic function is constant, you have a comparison function. And this looks like a comparison which you've got an epsilon to play with and another epsilon. You know what I'm talking about?
No, I'm sorry, I don't know.
Yeah, we'll talk about it after. It looks like a mimicking of an argument in classical analysis where you're proving.
I'd be interested because it's really it's specifically about entropy that
it looks like a comparison.
Yeah.
Measure.
Yeah, I'd be super interested to talk with you about this. So what do we have to do for the hyperbolic group context? Well, we need to deal now with the fact that we have cancellations. The issue is now we are not and this is the reason I did this so pedantically, because we have to now deal with the fact that we have cancellations. Then the theorem is, we use the fact that for hyperbolic groups, random walks essentially look like a sequence of, have a sequence of pivots, where the lengths in between these pivot points behave additively up to, a bounded constant. So if I look at these times, the lengths will actually, behave in, sum in the same way we would hope they are summable. And then we're just basically going to look at these increments. Some of them will be short. And again, that's where all our gains are going to be. The fact that when we take a bunch of short things and we add up their lengths, we do well. And if you're not short, I will basically literally tell you every single thing that happens. I'll say, actually what walk is doing here is doing this, 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 and this. And then you'll understand how the length is behaving. So I'll just condition on every element other than, these short ones. Right? Like, right, and then you'll also condition on, you know, where these cutoff points where you behave roughly constantly are. Again, you can choose these cutoff points sort of arbitrarily sparsely. All this other information is going to be less than epsilon n, saying the cutoff points, saying all these big words. And then you're left with summing up things, which is again going to be logarithmic. So this works in general for hyperbolic groups. I don't quite have, right, and a much broader class of hyperbolic groups. I don't have time right now to get into the lamplighter thing, but I do want to say was my last minute. Again, the idea is you sort of like, right, the general heuristic here is you're allowed to condition on whatever the heck you want, as long as it has entropy less than epsilon n. So there I might as well just basically condition on what the random walk looks like on the base group. Every n steps, I can condition on every step where I turn on and turn off a bunch of lamps, right? And then the point is just, well, the lamp configuration is going to stabilize. So most of the time, right, like it'll stabilize, you know, within a constant time after going to a right position on the base group. So that's enough. All right. I think that's everything.
Questions?
Is this written up?
Yes.
Okay,
Yes, these are both on the archive.
very interesting.
When you speak about pivots, right, you explained a little bit. Do you use this argument like in Giullio's work about pivoting?
We do use this argument in Giullio's work where he gives concrete estimates just because it was easier at the time. I think as you've remarked, as Kunal has remarked, you can actually get away just using Poincare recurrence. You really don't need almost anything here. You just need that, right? The fact that these pivot times exist, at least loosely, is doesn't require any actual machinery.
It's just I wanted to ask, you explain us a little bit the pivoting, but there is another difficulty already, even for free semigroup that I believe before your work was in the work of Giullio and Behrang
Yeah.
for semigroup, right? So
Well, we gave a full proof of semigroup. Right, it's not quite their proof, but we did give a full proof. Right, I mean, the way you make it even easier is you just cite showcase need and don't do this thing explicitly, but right. It's really, no, for free semigroup, it's actually just extremely short. But again, all these things are crucially entropy arguments, and we have no idea how to do them when they're not entropy arguments.
even for free semigroup, right? No equation at all, nothing cancels, no pivoting, everything obvious. You just don't have cancellation, you just multiply your words even here without entropy, right? We don't know.
Yeah. That we really don't. Like, right, how do I put it? It's not just that we don't know that this boundary, there's no consensus in the area whether it should be the boundary universally or not. I have switched my opinion on this multiple times, so I don't want to make any claim, right? So people of the last talk were asking whether there's any evidence. I don't think there's great evidence either way. Or right, the issue that's right, of course, right, if you say finite entropy, why should it just be finite entropy? But also we know that finite entropy for random walks is a very important cutoff, and all sorts of exotic phenomena show up in infinite entropy that can't show up in finite entropy. There's a lot of examples of it.
But are there sort of amusing examples of sort of random walks with huge steps which have interesting behaviors?
Oh, yes, absolutely. Let me give a few fun examples. So first of all, every finite entropy random walk that's non-degenerate, right? Like I won't, right, let's say generates a group as a semi-group. On the three-dimensional lamplighter is trivial, but every amenable group has a boundary, some measure which is non-trivial. So, or sorry, some measure with a boundary that is trivial, right? So you can find something that's different there. Also, there's a fun example, which is, right, if I have a random walk, I could like look at the left random walk, you know, where I multiply as I did, or I could also define the right random walk, where I just, you know, put the multiplication on the other side. There are examples of measures where the left random walk is trivial and the right random walk is non-trivial, or vice versa.
And this can happen only for infinite.
Yes, it can only happen for infinite entropy measures because, of course, when you look at the entropy can't detect whether it's a left or a right random walk. So that's right? Some amusing things. We know of examples where you can sort of get interesting stabilizers, right, of the Poisson boundary, where by interesting, I mean some elements which stabilize some of the Poisson boundary, but not all of it. Right now, the only examples we know of are for infinite entropy random walks. We don't know how to do this for finite entropy, but again, that's also open. Yeah, I know. I mean, there's all sorts of, right, the worlds are fundamentally, right, sort of very different. Infinite entropy lets you do all sorts of weird things that are just not possible in finite entropy. So that's why I'm not sure whether this is the same thing. But of course, that doesn't mean, right, the fact that you can do a bunch of interesting things does not mean you can do this interesting thing.
Okay, let's thank Josh again.